This video will be going over the OAM Server Tiler, the OAM Server Publisher, and the OAM Server API components of the Open Aerial Map server. So what the Open Aerial Map server does is it allows us to pull imagery off of the Open Imagery Network and produce a mosaic of that imagery that combines potentially overlapping imagery onto a map. So let's start with the tiler. The tiler is some code that runs on Amazon Elastic MapReduce, and it consists of two steps. It's a chunk step, which is a Python PySpark application that takes in the imagery based off of some request that's stored on S3 and tiles that imagery out into Web Mercator tiles that are at a zoom level based on the imagery's incoming resolution. And we'll take a look at that code in just a second. And then the second step is a mosaicing step where we take those individually tiled images and then combine those images based on an ordering that's determined by the order of the images that come in for the requests. So for example, if these two images overlap, the pixels of this image will have a higher priority, or end up on top of the pixels for this image. All right, let's look at the code. So if I'm in OAM Server Tiler, the chunk.py looks like this. So we'll start looking down at the bottom towards here, which is just a Python application that runs this Spark job. So all the functionalities here. So to run a Spark job in PySpark, you have to import a couple of PySpark things. Actually, you just have to import this. This is for creating an accumulator param, which I'll talk about in a second. What happens is the request comes in through a command line argument. So it's just some JSON, and we parse out the request JSON, and this is just handling either on reading from a local file system or reading off of S3. And once it parses the JSON, it just takes some properties out of that map. And if you notice here, we have this publish notifications boolean that you can turn off in case you're debugging and you don't want to publish to SQS. But we normally do want to publish to SQS, so we notify the start. I'll talk about the SQS elements of the jobs in a little bit, but the first thing we do is we create a set of URIs that represent the source images and some of the different paths that we're gonna use. So let's take a look at this function here. Great. So we have the list of images and then this workspace URI. Both steps, or the EMR steps, are gonna have need a place on S3 to sort of put temporary files. And I'll actually show that to you in the S3 bucket. So I'm inside of the OAM account right now. And you can see in our OAM account, we have this OAM Server Tiler bucket that has a workspace. And this is where some files will happen during the tiling job. And a thing to note is that in the life cycle of this bucket, we have delete workspace files. So that, can you view this? Yeah. Every 2 days, it cycles out. So imagery stays there for about 2 days and then it gets cycled out. Right. So we take our source URI. And then this VSI Krillify call will happen because we're using GDAL under the covers using with Rust Stereo, and we need to turn any sort of URI that looks like this, and then turn that into a VSI curl call, which looks like this. HTTPS, it would be bucket.s3.amazonaws.com image.tiff, right? So it gives you the VSI curl URI that you're going to be working with. And VSI curl, just in case you're not familiar with it, is a driver that lets Google read raster data from a remote source, and it uses the HTTP headers that allow you to read runs of bytes, like a specific range of bytes, to not have to pull down the whole entire file in order to read information from it. So for instance, if you're reading a geotiff, it'll only read the header tags in a Google info call and not have to actually read any of the image data. So if you have a giant geotiff on S3, you can call Google info on it and it'll only read a small section of that geotiff. All right. So here I'm just constructing just a set of URIs that I'm going to need later, and into this named tuple where we have the source URI, the workspace target, which is where I'm going to copy the image to, the workspace URI, which is the VSI curlified version of the target, and then the image folder is where I'm going to put this first stage images, and then the order is just the order in the lists that this image source this image source comes from, so that later we can know the order of the images that we want to for the mosaic step. Great. So if we just go back to that, we just get the count. This is some Spark stuff. Just get a Spark configuration, set the app name, get a Spark context. Accumulators, I'll go over in a second. Right, so the first thing we're really doing with Spark is to parallelize the URI sets, and giving it this image count parameter tells it how many partitions to create in the RDD. So we're going to have one partition per image set. And then we map that into this URI set copy, which just copies the source URI into the target workspace. So we actually create a copy of. It looks like the delete is working. Okay. It creates a copy of the image into the working directory, or the working folder. This speeds things up and means that we won't be hitting the Open Imagery Network unnecessarily. We then take the sets, the URI sets, and create image sources off of this. This create image source call just create image sources, creates a set of image sources, and then also uses this accumulator to accumulate the image sources. So what an accumulator does in Spark is it's almost like a shared variable that you can use inside of a closure, inside of a Spark task, to sort of shove values into, with sort of like an additive property. So each one of the RDD map tasks is going to add its image source to the accumulator. And then when the Spark job runs, that accumulator will be set with the values that it's accumulated throughout the run of the job. And that allows us to sort of do this this map reduce step, this aggregation of data step, that piggybacks on the execution of other tasks and other stages and other jobs in Spark. So that what happens is I map to create the image sources, and then I process them further, And at the end of the day, I can get my image sources from this accumulator. So that's a custom accumulator. To declare a custom accumulator in Spark, you would use this code. And really, this is just appending sources, image sources to a list. So it just collects all the image sources. So here we have the image sources, and then we're going to call flat map on that. And flat map on an RDD is something that takes it's like map, and where map would take one element and map it to another element. The flat map takes the element and maps it to a collection of elements, and then the RDD is just one collection that is sort of the flattening of all of the individual collections that were mapped to. All right, so we have this lambda image source generate chunk task. Let's take a look at that. Chunk task. Yeah. All right. So a chunk task is really what we're going to be doing with the tile processing. It's a task. It sort of describes the reprojection of this image into one of the tiles that that is its one of the tiles that is at its zoom level. I don't think we looked at create image source, but create image source actually uses Rasterio to get some information about the image, right? And it does that sort of Google info call where it doesn't actually pull down the whole image if it's a well-behaving geotiff. And it calculates some transformations like the lat long bounds and the web Mercator transform for this image. It also calls this get zoom call, which based off of the tile dimension and the resolution of the raster that we read using Rasterio, it'll get the zoom level that's appropriate to best match that image's resolution. And this is again a named tuple of all of this information about the image. So with the generate chunk tasks, we have this this zoom that we capture from the image source, and then we use mercantile to iterate over the min and max. Mercantile actually will give us the min and max tile for the image source that image covers in that zoom level. So we just iterate over those values, and then get the lat long bounds for the tile using mercantile. And we use Rasterio warp to transform the bounds from lat long to web Mercator, and so that's going to be our resulting target web Mercator bounds for this this tile, this chunk task. We get an affine transformation, and this is going to end up being the metadata that we'll set into the destination raster for the Rasterio for the reprojection call, which we'll see in a second. And there's the target, right? We have just the zoom level and then the tile call, tile row. So it's just that ZXY format, and we're keeping it in geotiffs. Right, so we have the generate chunk tasks. Right, now we have this set of tasks. And this is a chunk task is for every image, for every tile. It's just a collection of tasks that need to happen. So I want to know the count. I want to know how many tasks happen. So I'm actually going to cache this RDD so that it'll compute up to here when it does the count, but it'll save off this information so that I don't have to recompute those pieces of data. So this is actually one job. This will kick off a Spark job and give me the count of elements. And I do that so that I can just repartition the RDD into some sensible number, since it had one partition per image prior, and now I've generated a bunch of chunk tasks, so I want to repartition my RDD so that I take advantage of parallelism as much as possible and keep the task time to around 500 milliseconds, or as close as possible. That's a good rule of thumb. So I repartition my chunk tasks, and then I call for each, which is an action, a Spark action for each process chunk task. So this will again run this job. And image sources. This accumulator now has a value. Now that a job is run, I bet even if I put it up here, because this is an action, this image sources would have a correct value, but keep it there. So let's look at how we process chunk tasks. Process chunk. All right. So this create options just says, what we're gonna have for each of these web Mercator tiles. These geotiff tiles are going to be in web Mercator. They're going to be geotiffs. They're tile geotiffs with I guess I don't put in the block size. They're going to have deflate compression with a predictor of 2, and sparse is okay. So we open up that the task source URI, which is the copied workspace version of the image. And then we're going to copy the metadata from that image, update it with our creation options here, and then update it with the task target metadata that we created up here, which tells us, the height, the width, and the actual position on the map of the tile that we're about to create. Here we're taking advantage of the VSI mem driver for Google, which allows you to use a chunk of memory as if it were a file system to write rasters to. So similar to VSI curl, but just using memory instead of a remote location. And so we're going to open up this memory buffer with rasterio that we're going to write to. And we actually are going to collect each of the reprojected bands for each of the source bands into NumPy arrays. And the reason why we don't just go directly into the raster, because we could write the warp data directly into the raster bands, is because we're going to just do this check to see if there's any data in any of the bands. And this just prevents us from writing out no data tiles. We just kind of ignore those. And then so we go through each of our NumPy arrays and just write the band into the temporary memory result. And then we use the virtual file to buffer on the temp path to get the contents of the geotiff as a byte array. And then we say write bytes to target. Write bytes to target. We'll either write it to the local file system or write it to S3 using Bodo 3. Okay, and there you go. That really just writes out those tiles for each of the different tiles that we need from the image. And then at the end of all that, we collect our image sources. We construct image info, which just takes the image sources and then kind of gathers data that we want to know about each of the images. And then that gets wrapped up in some result JSON, and that gets saved off. And it gets saved off the local file system if that's what we're working with, or onto S3. And then it'll be done. So there's a notify of the success of the job, a notify of the failure of the job, and then also a notify of the start of the job. So this notification is just SQS notifications, right? We just have some JSON messages that we send off to an SQS queue to be processed by the publisher component, which we'll go over later in the video. Great. So to take a look at To take a look at what one of these result JSONs look like, let's open this up. Great. And then go to JSON lint. So we can see that we have the job ID, which is the job that just came in from the request. The target came in from the request as well. The tile size is what we chunked it out to, and that's just a constant in the chunk.py script. And then here's the input images. We actually give the grid bounds, sort of row max and row min for the tile coordinates of the image, because we're going to use that in the second step. We give the lat long extent, although I don't think that's used in the mosaicing anymore. The source URI is actually the VSI curl version of the source URI. That's a bit of a bug, probably. And look at that. And the max, the zoom level that it's coming in at. Great. So that's the Python chunking version, right? So let's talk a little bit about how to run that. So we have this run local chunk shell script here. And with PySpark, you just straight up give it the Python file. Say, okay, chunk.py, run it. And then this test request local is just what it would expect off of S3, but this is, off of a local file system. And the workspace and the target and the images are all local. So if I ran this, I would get some local chunked images inside of this workspace folder. Great. So next on the list is the mosaic step, which is in Scala. And so let's go over that code. Inside of Mosaic, we just have an SBT script that you can use to run SBT and build everything. So this is just sort of regular Scala project. Organization. In our resources, we have an application.config, a couple other things. This is where I set the SQS queue URL and the region. Okay, so a lot more code here, or at least broken up into files. So let's go ahead and go through that. That's not what I wanted. Main. So here is main. We're just getting a Spark context. We're using setIfMissing to sort of set the local values if it's not already set by Spark submit. So we read in the job request, which is that step 1 result stuff, either from S3 or from a local file system. And here's the same sort of thing. We're publishing a status, and the status is using SQS to send either a start status, a failed status, or a finished status. And the finished status for this one will actually set the source URIs, because that information gets carried forward. The input images come in from the job request. We create a sync, which is just a method of saving off the PNGs as we generate them, either local or S3 again. And then we call the tiler with the sync that we created and the input images. And then this, again, will publish failure or success. So let's look at the tiler and see what it does. We have this apply here with the implicit Spark context. So tile counts is a class that allows us to count the number of tiles at a specific zoom level for a mosaicing job. And the reason why I did that is because if I can mathematically compute via the grid bounds how many tiles that I'm going to have at any point in the mosaicing process, I'll know exactly how to partition my RDD to maximize parallelism. So that's about all I'm going to say about that code. It's what allows me to know how many partitions to make, and it's used inside of the tile partitioner factory. Right, I give this a target tiles per partition and a tiles count, and it basically counts for either merged or unmerged collection and RDD of tiles. It will give me a new hash partitioner that is of the correct size. So that's sort of an optimization, Spark optimization that I put in, and you can read through the code if you're interested in that. So here we're creating one of this partitioner factories. Zooms to tiles is just taking the input images. One thing to note about the input image RDD, when we were in main, and we got the job request, this input images is from the job request, but that's actually sort of computed. So these input images, what comes in from the job request is a set of input image definitions, which is, looks like that. Information like, this. And then so to actually create an RDD off of this, it actually uses this tile service reader to read in the image tiles at a specific zoom level. And then so what this code does is it says we're reading in 1024 by 1024 tiles, and we're targeting 256 by 256 PNGs. So in order to work with the incoming tiles, I just immediately split them off into 256 by 256 chunks. You get a new zoom level, right? Because a zoom level 1024 by 1024 tile is a zoom level, what is it? Did I say 10? So 12. A zoom level 12, 256 by 256 set of tiles, and there's 16 of them. And their tile IDs are going to be different. So that's what this split function does on input image RDD. Is it takes the image and it basically just iterates over all of the tiles that you want to split it into and creates a new spatial key for those smaller tiles, and then crops the larger tile into smaller tiles. Great, so that's how we create the input image RDD. So if we go back to the tiler, we see that we have these input images. And this grabs ordered images. So in ordered images, if we go back to input image RDD, order images is just a property hanging off of this that just takes the images and maps the values. So we keep the key, but we turn it into this ordered image. And an ordered image is a image composed with a tile that is basically a mask tile, sort of, that contains the order of that image in the mosaic. So it's a constant tile when you start out because each image just has has only one source. So its order tile is every pixel of the order tile is going to be the same priority. So that's what you see here. And then a constant tile in GeoCharles is just a single value in memory. but it acts like as if it was a whole raster of that single value. So we get the ordered images, and then here's sort of where some logic happens, where if we have a set of input images that were of the same zoom level, then we kind of want those we want those RDDs, those separate RDDs, to just be one RDD. We don't care at this point, because we have the order of the images baked closely to the actual image. We no longer care where the image came from. We just want them all in a collection that's sort of indexed by the zoom level that they're at. So that's what this is. That's what this is doing. It's just creating a map of our zoom level to the RDD of spatial key and ordered image. And we sort that by zoom, descending by zoom, because that's how we're going to process the imageries. And then we create a sliding window of so this is just the zooms. And then we create a sliding window of the zooms, because if, say, we have like zoom 18 imagery and zoom 14 imagery, and then zoom 12 imagery and 5, we'd process them sort of 18 to 14, 14 to 12, and then 12 to 5, and then actually 5 to 1. It's just why that you see me add the zoom level 1 right there. So it creates just sort of sliding window of how we're going to be processing this imagery. So zoom groups, we're going to just do a fold over that. And then this logic just takes the previous tiles that were from a previous zoom step. So initially there's just none. And grabs the new the tiles that have a max zoom level of Z1. And then go ahead and then do that partition factory, figure out how many unmerged tiles are going to be at that zoom level and partition accordingly, and then process this RDD, because we have all the RDD that we need to process between the zoom level 1 and the next zoom level that actually has source imagery at that max zoom level. So there's not going to be any new imagery that comes in between these two zoom levels, so we can just process the tiling between that. And we have this create sync function, and the create sync function is, I could just pass a sync through, but that's because of the way the closures work. You want to actually new up a sync closer to the like inside of the map task. So we're passing in a function that will actually create one of those syncs. So process between is a function that is implicitly added to our RDD via this implicit class. So process between, here we go. We're going to take the images and we're going to reduce by key. So this means that, if we have an RDD that has images from multiple sources, but they overlap the same area, then they're going to have this same key. And then, so when we reduce those, we're sort of smashing the tiles together using this function orderedImage.merge. So orderedImage.merge is just something that pays attention to the order value of each of the tiles. So if I have two tiles and one's partially no data and the other's partially no data, so I'm going to set some. It's kind of a tricky logic to think through, but if you think through, you're merging two tiles and they have different priorities. Each of those pixels has a specific priority, and then the pixel that has the higher priority wins, and then that order is set into that pixel for the new order. So that's sort of the merge. That's the mosaic functionality that we have right now. As far as expanding on this mosaic functionality, because we just get this like order object for each pixel, we can actually use different logic rather than just O2 is greater than O1. If these represented image IDs or some other properties about the image that we can use to decide which pixel to take, then that's where that logic would go. And then so we save, we call this save on this RDD, and that's something that's implicitly added through this implicit class. We take the images, and I'm just mapping over the partitions and sort of just giving back the exact same value. And so instead of running a job and saving off images and kind of syncing them as like a for each call, I'm just going to do a map call so that I can have the save sort of be a no-op map, but it actually does the processing of it and is sort of like a stateful map, which I think is a no-no in purely functional languages, but that's not what we're dealing with, so that's fine. What it does is it saves me the headache of like figuring out if I should cache an RDD and then do the for each and then continue using the RDD. It sort of just puts the save into a pipeline that you still end up with one job, and that's useful and I think more performant in Spark. Great. I think that should explain this Tiler code. The algorithm of processing between zooms is a little complicated, but perhaps if I had a whiteboard, I could explain a little better. But that's about all I'm going to go into today. Sure. This tile service reader is something that you just give like a URI, like an S3 URI, and then you read a zoom level out of, and it just uses S3 to list the buckets and then figure out the number of partitions and then use the client to read each image. It's not particularly exciting. So I think that's all I want to say about the the Scala code. Besides how to build it. So really what you want is the assembly that you can run through Spark Submit. So if you use that SBT script inside of the mosaic, you get the assembly. Great. You can see where it's at. And then to run this locally, there's a script called run local mosaic, which just has some like comments. I don't know, 13 minutes. I guess it took 13 minutes to run once. That's fun. And then gives a little bit more. But this is the running the jar under this step 1 result. But running it locally is not the fun part. Running on an EMR is. So let's now talk about the setup for running all of this stuff on EMR.